There are many different types of equations that you can come across, and we're going to look at just a few of them here in this video. So first off, if we have fractional exponents, if we can get them by themselves, then we can use like inverse powers. Now we're going to get two answers if we have an even numerator, because it's the same reason like if you take a square root, you have to add a plus or minus. It's the same process. So this is because, again, x squared equals 4 when x equals 2 and negative 2. There are two numbers that give us that. But x cubed equals 27 only has one solution, x equal to 3. Okay, now let's look at this case here. We have z minus 8 4/3 power minus 256. To do this, I'm going to get the whole power term by itself. So z minus 8 to the 4/3 equals 256. And to get rid of this 4/3, I'm going to take the inverse powers. Now I could do both sides by 3/4 and continue, but I'm going to take it one step at a time to show you this whole even numerator power thing, because we do have an even in the numerator. So the first thing I'm going to do is I'm going to take the 4th root of both sides. So the 4th root of 256, because it's an even root that we're taking, we have to add in a plus or minus. And the 4th root of 256 is what times what times what times what equals 256. That's going to be, I believe, 4. Let me double check that. Yes. So we're going to get to the 1/3, or the cube root, equals plus or minus 4. And now all we have to do is take the 3rd power of both sides. And that's, of course, going to give us two equations. The positive 4 cubed is 4 times 4 times 4 is 64. And z minus 8 equals negative 4 cubed. Negative 4 times negative 4 times negative 4 is negative 64. At this point, we can just add 8 to both sides. And we're going to get 72. Or, let's see, negative 56. And those are my two real answers. Now, let's check this on the graph. I'm going to graph this equation here that I started off with when it's equal to 0. We know that this is only true when it touches the x-axis. And that happens here at negative 56 and positive 72. It's kind of a strange graph. It has a weird point there at the vertex, but that's the idea here. Now, interestingly enough, this equation actually has more than just these two solutions. I'm not going to talk about how to find them, but it actually also has 8 plus or minus 64i as solutions. And I recommend you check that yourself. Plug it into the equation, each one of these solutions individually, and see that you get a true statement. Okay, for this next one, I'm going to do the same kind of process. I'm going to get the variable with the power by itself. So I'm going to subtract 30. Let's see, 1/4 m to the 7/2 minus 13 equals 14. Divide by 2. Add 13, then I'll multiply by 4. Okay, now I can multiply by 4. That's going to give me m to the 7/2 equals 80. And at this point, I can just take the power of 2/7 to both sides, or I can take the 7th root. I don't have to worry about two answers because we have an odd power in the numerator. So either way, it's going to be fine. I don't think it's going to be really any nice form for this one. I'm just going to do to the 2/7. Those cancel, and we get m equals 80 to the 2/7. Now, of course, this equals two different things. This equals, well, they're both the same, I should say. 80 squared to the 7th root, or the 7th root of 80 squared. And I recommend the second method because when you take the 7th root of 80, you get a smaller number, and squaring that is going to be easier to do. If you take 80 squared, it's going to be a large number. And yeah, it's just easier to work with smaller numbers. So let's go ahead and try it out. 7th root of 80 is about 1.87, and then squaring that, it's going to give us approximately 3.497, something like that. 3.497. Okay, let's go ahead and graph this thing. I'm going to subtract 44 from this side to the other side to make it equal to 0, so that the answer is going to be the x-intercept. And the x-intercept of this graph, kind of a strange graph again, kind of like a square root almost, but that's been flipped. It's 3.497, 3.497. That's what I got. Now, just like in the previous one, there are more complex solutions. But we're not going to talk about finding those complex solutions. The real ones are really what we're looking for in this case. Okay, now if we have polynomials and they're simple enough, our factoring strategy that we use for the quadratic will also work. But this only happens if they actually can be factored. So I'm going to do this by getting everything over to one side and try and factor it. So I'm going to subtract 12v squared, subtract v, and add 27. Okay, that gives me 0 on the one side. We get 4v cubed minus 12v squared minus 9v plus 27 equals 0. I made sure I wrote from highest power to lowest power, and then I combined like terms at the same step. And this is a more than 3 terms. It's not a monomial, binomial, or trinomial. So the best thing we can try here is factoring by grouping. So from the first 2 terms, I can take out a 4v squared. That's going to give me v minus 3. And from the next 2 terms, I can take out negative 9. That's because this is negative here, so I'm going to take out a negative. That's going to give me v minus 3. Okay. I get v minus 3 when I take that out. What remains is 4v squared minus 9. And 4v squared minus 9 is actually a difference of 2 squares. It's 2v squared and 3 squared, which means I can factor it further into 2v minus 3, 2v plus 3. And this has 3 solutions. When each one of these is equal to 0, this one equal to 0 gives me 3. 3 minus 3 gives me 0 here. This one equal to 0, you can just set it equal to 0 and solve if you want. I'm going to add 3, then divide by 2. We're going to get v equals to 3 halves. And this one's going to be the same thing, but now flipped sign. So v equal to negative 3 halves. So I get 3 solutions here. All right, this is a 4th power. Once again, I'm going to get the variables over to one side. I'm going to add 3w to the 4th over because that makes it positive. And I will work with positives if I can. So we get 3w to the 4th plus 81w. And I can divide out by 3 from both things. So it'll give me w to the 4th plus 27w. And I can factor this side. Now I can take out a w first. W cubed plus 27. And w cubed plus 27, 27 is 3 cubed. That means this is a sum of 2 cubes. So I can factor it down immediately into w plus 3, then w squared plus 3w plus 9. I just used that algorithm that I described in that previous video. Okay, now This is going to have two real solutions, w equal to 0 and w equal to -3 from this portion and this portion. This portion is going to give us two complex solutions, which we can find using the quadratic formula. I'm not going to worry about that here because I want to show the real solutions shown in the graph, and that two more are not shown. But it's important to note that there are four solutions for this problem. Two real ones, 0 and -3, and two more complex ones that are given us from this w squared plus 3w plus 9. Okay, let's look at this thing on the graph. The first one, once again, I just moved everything over to one side, and graphing it, you can see that it's equal to 0 at -1.5, that's -3/2. 1.5, that's 3/2. And 3. That's the last choice there. So we found all of our solutions with this graph. Now looking at the next one, you can see here, let's see if I can zoom out far enough. It's kind of a tall shape there. You can see here that we have 0 and -3, 0 and -3, and there's not going to be any other ones. Let's go ahead and change the x-axis. Something really large here. And you can see you can't see it anywhere besides these 2 points. 0 and -3 are there. If you go left and right, you're not going to see anything. We can actually see the look of this graph by going to a smaller x value, but then a much larger y value. And this is the kind of graph it looks like. Once again, it's a little strange, but it's going to keep going downward to the left here and keep going downward to the right here. It's never going to turn back around. So 0 and -3 are the only real solutions. Now, we got 3 answers from a third degree polynomial and 4 answers from a fourth degree polynomial. This is always the case, so keep this in mind. Okay, for the next one, we're going to look at radicals here. And for this one, we're looking at specifically square roots. And the way we can solve these is getting the root by itself and squaring it. That cancels the square root, and then we can continue. And we may have to do it multiple times, like in this problem we're going to have to do. So first off, I'm going to add u minus 3 to the other side. Well, the square root of u minus 3. That's going to give me 3u minus 12 by itself. And now I can square both sides. And when you square both sides, you're not squaring each term individually, you're squaring the entire side. And that changes how you simplify, because now we have to expand this binomial. Right? It's going to be it's going to be 1 plus root u minus 3 times 1 plus root u minus 3. We're going to get 1 plus 2 root u minus 3 plus u minus 3, because it's going to end up being squared. Okay? And you can see we once again have a square root underneath of it. So we need to get everything away from that square root and then square it to get it to simplify. So subtract 1, add 3, and then minus u. That's going to give me 2u minus 13, so minus 10 equals 2u minus 3. I can divide by 2. That's going to give me u minus 5 equals the square root of u minus 3. And once again, square it. Okay. Now on the left-hand side, u minus 5 times u minus 5 is going to give us u squared minus 10u plus 25. On the right-hand side, we get just u minus 3. And now we can get everything over to one side because this has now become a quadratic equation. Okay, we can factor it. Let's try a times c is 28, minus 11 is just b. Two numbers that multiply to give 28, add to get a negative 11. 7 and 4, I think. Yeah, negative 7 and negative 4. So we get u minus 7, u minus 4. I can use a shortcut because a here is 1. That gives us the solutions u equal to 7 and u equal to 4. 7 minus 7 is 0. 4 minus 4 is 0. That's what gives us the solutions. So we have two solutions here. And it's important to know that most likely at least one of these solutions will be what's called extraneous. It's a fake solution that comes up when you do this process. And so only one of these two solutions works, typically. So we need to test these values. And you just test them by plugging them into the square roots here. 3 times 7 is 21. Minus 12 is 9. So we have the square root of 9. 7 minus 3 is 4. The square root of 4 here. The square root of 9 is 3. The square root of 4 is 2. 3 minus 2 does equal 1. So 7 works. But when we plug in 4 into here, 3 times 4 is 12. 12 minus 12 is 0. We get just 0 here. And here, 4 minus 3 is 1. And the square root of 1 is 1. We have negative 1 equals 1. And that is how you know that 4 is an extraneous solution. It gives you a false statement. The reason why it came about is because we had to square both sides, and that gave us a quadratic equation, and quadratic equations always have two solutions. But this equation only had one solution from the get-go. So we added in a second solution by doing this algebraic method. The nice thing about checking your work geometrically on the graph is you only get one solution, the correct one, 7. So always make sure you check your solutions by graphing. And of course, once again, always make the equation equal to 0. I subtracted 1 from this side to the other side so that it's equal to 0. That way, all you have to do is find the x-intercept, and that's your solution. Now, if our equation can be rewritten as a quadratic, we can use quadratic strategies to solve. And this first one, I can rewrite it as y equals x cubed, because now if I square both sides here, I get y squared equals x to the 6th. X cubed squared is 2 times 3 is 6. That means I can change this thing down into y squared minus 7y minus 8 equals 0. And this is quadratic. So I can try the AC method real quick. Negative 8, negative 7. That's going to give me negative 8 and positive 1. I can use a shortcut method here since a is 1. That's going to give me y minus 8, y plus 1 equals 0. And I get solutions y equal to 8, y equal to negative 1. Of course, this isn't our final solution because our variable was x, not y. We have to substitute back our what y equals, which is x cubed. So x cubed equals 8, and x cubed equals negative 1. Now we can take the cube root of both sides for both equations. And we see that actually our solutions are 2 and negative 1. That's the important thing to note here, is that you have to always plug back the original equation again, or sorry, the original variable again. If you don't do that, you're going to get the wrong solution. Now for this one, I need to get it equal to 0, because I'm going to try and make this a quadratic, and you have to have it equal to 0 to solve that. So I'm going to rearrange this so that it's going to be x to the negative 2, then minus 5x to the negative 1, then minus 6. And here I can see that y equal to x to the negative 1. If I square both sides, I get y squared equals x to the negative 2, which gives me y squared minus 5y minus 6. AC method once again, -6, -5. This one's easy, -6 plus 1. Once again, I can use the shortcut method, y minus 6, y plus 1 to factor it. And that gives me two solutions, y equal to 6 and y equal to -1. Going back, plugging back y into there, y equals x to -1. So I get x to -1 is just 1 over x. It's just a reciprocal, right? So you have 1 over x equals 6. 1 over x equals -1. I can flip both sides of the equation, giving me x equal to 1/6 and x equal to, well, 1 over -1 is the same thing as just -1. So that one's quite easy to solve. Okay, so this is really just about factoring, figuring out what's the substitution you have to make here. And the first one was y equal to x cubed, and then y equal to x to -1. And then making sure you plug back the original variable into the equation and solving. So let's check these real quick. For the first one, you can see I get a polynomial graph here, -1 and +2. -1 and +2 are solutions. And solving for the other one, we got -1 and 1/6. Kind of a strange graph here, but we get 0.167. Type that on a calculator. 1/6 is 0.1666 repeating, so 0.167 rounded, that's correct. And then -1 is our other solution. So that is correct. And it will not cross the x-axis again, to the left or the right. Those are the only two solutions there. All right, here we have an absolute value equation. So we can solve it like we normally do for absolute values. We're going to split it up into two equations. The absolute value is already by itself, so we can just go ahead and split it up. We're going to have the positive version and the negative version. So the positive version is the exact same thing without any changes. Just drop the absolute value. And the negative version is everything the same on the absolute value, but now we make 13 negative. And this is a square root equation, so we can solve it by getting the square root by itself and then squaring. I'm going to do that by adding the square root of x to the other side and then subtracting 13. I can do this very similar thing on this side, add the square root of x to the other side. Now I'm going to add 13 instead. Okay, that gives me 2x minus 36 equals the square root of x, and 2x minus 10 equals the square root of x. Now I can square both sides. So I have x equal to, I'm going to multiply this thing out. It's 2x minus 36 times 2x minus 36. You can do that on the side paper if you want. I can do it pretty easily in my head, I think. Let's see, it's going to be -72, so -144. X, I guess 36 times 36, I'm not too sure of. 1296. And now all I have to do is subtract x. And on this side, we're going to have 4x squared minus 40x plus 100 equals x, and subtract x. And here we have two different quadratic equations. We expect there to be two answers from this side and two answers from this side. I don't know if these will factor. Probably will not. You probably have to use the quadratic formula on each one, but they will both give you two solutions. And it's important to note that we expect at least one of the solutions to be extraneous because of this square root. Typically that happens when you're solving for the square root and you take the square. That gives you an extra solution normally. So I would expect two of the solutions, one from each quadratic equation, to be a fake solution. and there's actually only going to be 2 solutions in total. Now, instead of doing this whole process, you can, of course, graph both sides of the equation instead and look for intersections. Think of this like a system of equations where we have one equation here and then the other equation here, and where they're equal is the same thing as where they intersect. So that's what I have done down here. This is just the absolute value of that statement. And y equal 13 is the way Desmos needs it to be able to understand what you're saying. You can't just type in 13. It won't recognize that as a function. And if I graph that one, I get this weird check mark. And if I graph this one, you can see here that we have 2 points of intersection, 6.25 and 20.25. You're looking for the x values, not the y values, because x is our variable of choice. Y just happens to be 13 here because that's how we have to set it up. You can, of course, also just do subtract 13 from that, and that's the same thing as just asking where is it equal to 0. Same process, same idea. Sometimes this method, though, where you have 2 equations, is easier to use because the 2 equations might be, complicated, and you don't want to move things around between the sides. So, all right. Give it a try in number 1.